So this is lesson 3 in the functions and relations unit on function notation. So last time in lesson 2, we learned about what a function is, and we learned some key vocabulary that we can use like domain and range and independent and dependent variables to describe functions and relations. And we're just going to go a little bit further today and learn some new notation for functions and look at look at equations as well. Okay, so let's start with this example. We have here a graph which is representing a function. On the graph, we have time on the x-axis, and we have volume of water measured in liters on the y-axis, and it's measuring the volume of water in a pool. Okay, first question we ask here is, does the graph represent a function? Explain. From last lesson, we learned that a function is a relationship where each input value, in this case time, each time would be associated with only one output value, so volume. And that's the case here. There isn't a time where there are two different volumes of water. Every time has only one volume of water. And so yes, this is a function. Each time on the graph is associated with only one volume. Okay, I'm going to use today throughout the whole lesson here the color yellow for independent or x values, independent variables, and then blue for dependent values. So the independent variable here is the one we see on the x-axis, and it's our most common independent variable that we're going to see in this unit. In this case, it's time, and it's measured in minutes. When we're asked to define or identify a variable, we need to say the units if that's applicable. And then the dependent variable, so volume here depends on how much time has passed. That's why it's the dependent variable, and that's measured in liters. Okay, so here we're going to learn something new. So key idea. So often especially when we're using an equation, we use different letters to represent these variables. So in this case, we're going to use the letter V for volume, just because volume starts with V. So you'll see here a little V on the y-axis instead of a y. And then same here with time, we're going to use the letter T to represent time instead of X, just because it's a little bit more descriptive. So here, that's what we're saying here. We're going to use the letter V for volume. And instead of writing V, we can actually write function notation and be a little bit more specific. So we can write V and then in brackets a T next to it. And what that means in math when we write that is that we're identifying the variable volume, but we're also saying what it depends on. So in the brackets is the variable that volume depends on. In this case, it's time, right? And so here in the blanks, since volume depends on time. Okay. And when we say this out loud, when we're reading that, V and then in brackets T, we say V of T when we read that. Okay, so let's just use the graph here to make sense of this new notation a little bit more and read some values from the graph. Okay, so here in the first column of this table, we have a bunch of times. So I'm going to highlight them in yellow because these are the x values on the graph. Okay, and then we have some volumes. Some of them are blank, some of them we'll have to fill in. And then we have this new function notation that we're going to make sense of here. So let's start with the first one. It says 50 minutes. Okay, so let's go to our graph. I'm going to go to 50 minutes. This is right here between 40 and 60. I go up, I see that that point is associated with 100 liters of water. So the way we would write this in function notation is we would say the volume of water when the input is 50 minutes, at 50 minutes, is 100. So the volume at 50 minutes is 100 liters. So in words, that's how you could say it. But we use the function notation for short. It's like a quick way of saying the same thing, which would take a long time to write out in words. So it's a nice convenient notation to say something quickly to refer to a point on the graph. Okay, let's do the next one. So this time it's giving us the opposite information. They're telling us a volume. So let's go back to our graph. Oh, we see here 600 is at time 0. So that would refer to 0 minutes. So then V of 0 equals 600. So at 0 minutes, our pool has 600 liters of water. Okay, so you see the volume at 0 minutes is 600. Okay, here we have some function notation. I would encourage you maybe to pause the video here and try the last two on your own. Okay, so here our input is 30. When we input 30 minutes, the output is 200 liters, and we can see that on the graph as well. So at 30 minutes, the volume is 200 liters. We can write that in words. At 30 minutes, I'm going to write min for short. The pool has 200 liters of water. And the last one I like because we're saying it more like how you would say it outside of a math class. The pool's empty after 120 minutes. Empty means no water left, so the water would be 0 liters after 120 minutes. So sometimes in words you might not write it in the same order. So what we would say here is at 120 minutes, there is no water left. So the volume at 120 minutes equals 0 liters. That's how we would do it in function notation. So it's just kind of a shorthand way of referring to a point on a graph. Okay, so let's do it in an equation. This is our second example here. So now we have an equation, and I'll just read it here. It says C equals 42.5 times N plus 630, and it represents the cost of renting out a restaurant, where C is cost in dollars and N is the number of people that attend a party. Okay, so the first job here is to identify the variables. So now when we have a relationship that's in an equation, the output is what the answer is going to be. The input is the independent variable. So here, the cost is going to depend on how many people come to our party. So the cost depends on the number of people that come. That makes sense, right? So here, the cost is going to be our dependent variable, and it's in dollars, right? And we're calling that C. So I'm going to write that here. And independent variable is the one you see within that equation. That's the input value. That's what we would put along the x-axis if we were going to graph this. And that's the number of people. When we're counting something in math and there's like a number of something, often we use the letter N when we're doing that. Okay, so this equation is not written in function notation. Notice I don't have those brackets, right? So there's a really quick, just a slight change we need to make to include function notation here. So all I have to do instead of writing C is just write C of N. So the equation is the same. The operations are the same on the right-hand side of that equal sign. The only difference is I'm just being a little bit more specific with my dependent variable, and I'm just saying what it depends on, right? So instead of just saying C, I'm just saying C of N, meaning that the cost depends on N. So when you input a number of people, you can get a cost. So let's answer some questions here now that use function notation. So here it says determine the value of C of 35. Okay, so C is the cost. I don't know that, but I'm inputting 35. So this is the first time we're using one of these equations. So I'm just going to rewrite the equation here so we can look at it a little bit closer. So I'm just rewriting it. So what we're told to find is C of 35. So see how the N in that first expression was replaced with a 35. So what that means is our input number, our N, is going to be 35. So in the equation, I'm just going to rewrite the whole thing. But instead of writing the N, I always like to encourage students to use brackets. I'm just going to put the number 35. And this is where I can just take out my calculator and evaluate that expression. Now, one thing to remember is whenever you have a variable next to a number like that and there's no operation, that's multiplication. So I did put a little multiplication symbol in between there. So I'm going 42.5 times 35 plus 630. And the answer I get is 2,117.5. So what does that mean as a sentence? I'm saying when there's 35 people that come to my party, the cost is going to be that. So when 35 people come, people attend, and this is not the exact way you can write it, you can switch it around, but this is one way to say it. When 35 people attend, it costs, use a dollar sign here, right? Because we're talking in dollars. And for money, we typically use 2 decimal places. You wouldn't really see 0.5, so we're going to add a 0 there. So $2,117.50 is the cost when 35 people come to the party. And I'm sticking with my colors here. 35 people was the input. This cost was the output. Okay, let's do a question where we have to go backwards. So here we say, and this is a typo in the notes, determine the value of n, not d, when C of n equals 2,670. So this time they're telling me the cost. I'm trying to find the number of people. So let's set this up. So I'm just going to rewrite the equation again. C of n equals 42.5 times n plus 630. This time I know the cost. I know the cost. So I'm going to replace that cost on the left-hand side with that 2,670 that I'm given. And I don't know n. That's my goal here, is to find the value of n. I want to know what that n value is. How many people are coming to this party? So when we don't know the independent variable like this, it's within the equation, I need to use some algebra, some opposite operations to solve for it. I need to work backwards. When we're working backwards, we need to go in the opposite order of BEDMAS. So I'm going to start by subtracting, the opposite of adding there. Remember the golden rule in algebra, what I do to one side, I must do to the other to keep everything balanced. So that gives me 2,040 is 42.5 times n. And the opposite of this multiplication operation that's happening between the 42.5 and the n is division. So I keep it consistent by doing that division to both sides. That keeps, oops, sorry, that doesn't cancel out on the left side there. There we go. So when I divide 2040 divided by 42.5, I get exactly 48. And on the right-hand side, I just have the n, and that was my goal. I've now found what n equals to. So when I say this in a sentence, I could say when 48 people attend, the cost is $2,670. Should be careful to use units when you are writing these sentences, right? So sometimes you'll have to work backwards if you're given the value of the dependent variable. Okay, let's practice working with some equations that are more abstract, that they don't have any word problem associated with them. So when there's no real-world context for an equation, we just typically use the same letters for our variables that we've named our axes on a graph to keep everything consistent. So on a graph, we typically use x for the independent variable, right, on the x-axis, and then on the y-axis, the dependent variable, we just call it y, if there's nothing better to call it. So x and y, and that probably feels familiar to you, seeing the letters x and y in some equations that you worked with before. But instead of y, if we want to use function notation instead, we could write y, or we could use f of x. That same kind of bracket, and then f, the function value, depends on x. We use the letter f just because if we're talking about a generic function. Yeah, just because it starts with the same letter. So an example, let's say our equation was y equals 2x minus 5. This is an equation maybe you've seen before, maybe in Math 9. Instead of writing that, an equivalent way to write that would be f of x. The function value depends on x, and here's the equation that gets us that output value. These are the same thing, just different ways to write it. So this is called function notation, but again, they mean the same thing. You're just being a little more specific with what your independent variable is. So let's practice using function notation again. If you feel comfortable, you could pause the video here, because we did something similar to this with the graph on the previous page, or you could do it with me. So here in the first column, I have my x variables, and then I have my y variables. And then I have some ordered pairs, which hopefully you're familiar with, right? In an ordered pair, we're specific about the order. We first give the x value. So in these ordered pairs, these first numbers are all x values, and then the y values. And then we're just going to practice using function notation to describe the same points. Okay. So let's say I have 6 in my ordered pair there. I can tell the y value is -5. In function notation, I would say the function value when I input 6, that's the x value, the output is -5. Okay, so that's how I would write that same point using function notation. Okay, let's do the next one. And again, pause the video anytime and try these on your own if you feel comfortable. So when I input 13 here, the output is 4. The y value is 4. When I input 13, the y value is 4. So I'm trying to keep consistent with my colors. Okay, next one, I have the ordered pair. So 90 is the x value, 700 is the y value. So in function notation, I would say when I input 90 into the function, the y value or the output would be 700. Just a nice, quick, efficient way of describing a point. Okay, for the next one here, when I input -2, the output is 9. When x is -2, the output is 9. Okay, so let's try working with function notation with a more abstract equation. Again, pause the video anytime and try these on your own and then check back with me if you want. So this equation here, the y values are a dependent variable, x is independent. And in function notation, we'd write the exact same equation. It's just instead of y, we're just writing f of x. Okay, so here, that way we can ask these quick, efficient questions like what is the function value at 4? So what that's asking is what happens when I put 4 into this equation? What output do I get? So if my f of x is 2x minus 5, f of 4 would be 2 times 4 minus 5. So I'm just replacing that x in the equation with a 4, and I'm seeing what I get. So 2 times 4 is 8, 8 minus 5 is 3. So I'd write f of 4 equals 3. Okay. Now we're going to work backwards. It says, what's the value of x? So I don't know the input, but I know the output is -15. So let's pull up our equation. Our equation is this, 2x minus 5. Oops. So it's saying, what happens when the answer is -15? What value of x do I need to input here? So my goal is to find that x. So again, we need to use opposite operations. I'm going to start with adding 5 to both sides. That cancels out the 5. We want to ultimately isolate x there. -15 plus 5 is -10. And then we want to divide both sides by 2. So I get -5 equals x. So when I input -5 into the equation, the output is -15. So that's my final answer. Okay, so that takes us to the end of the lesson.